Okay, so welcome to lesson 3 of energy resources and energy transfer. So if you remember, we've been looking at types of energy, we've been looking at how energy is transferred from one type to another. Okay, so for example, I've got a little tea light here, we say in English. Okay, there is chemical energy stored in the chemicals, okay, biochemical reaction that's turning into heat and light energy. Okay, there's another reason why we're looking at this today. If this was an actual lesson, we'd sit for a few minutes looking at these candles and thinking about them. Okay, if I put my hand above the candle, I can feel the heat. Okay, now it's often says that heat rises, but in fact that's not true. Heat doesn't rise. What's happening is the hot air, the hot gases are expanding. This makes them less dense, so you've got the same number of particles in a bigger area, and so the cold air around it actually pushes that up. And we say that the heat travels by convection. So hot air rises, that's very true, heat doesn't rise. Okay, so this is an example of a convection current. The hot air rising. Now if you think about it, if the hot air rising, then cold air must be taking its place. Okay, so we're getting a convection current. Okay, let's see if I can find my slideshow here. Okay, so heat travelling by convection. So a hot fluid. In physics, a fluid is either a liquid or a gas. So it expands, it's less dense, so it rises. Okay, cold fluid takes its place, a convection current is formed. So when this video is finished, if you can come back to this slide, please, and copy these notes down. Okay, well, here's an example. So here's a picture of a volcano taken from a very high altitude aeroplane. And this is what's happening here. Yeah, the hot gases from the volcano, the hot gases of course contain lots of dust and things like that, are rising. Okay, and that's how you get that mushroom cloud there. When they get to the layers of the atmosphere above, sometimes they spread out. Okay, so there's lots of examples of convection here. I'm just going to go back to the video again. I've got my kettle here. In English, we use a kettle. It's an electric kettle. It goes on a stand. Okay, if you look inside. Okay, the heating element, so the thing that heats the water, is actually at the bottom of the kettle. It's at this layer here. Okay, and the reason is the water gets hot, okay, it expands, it rises, and cold water takes its place. So inside the kettle we get a convection current. Eventually all the water will get hot. If the heating element was at the top, what would happen is the water at the top would get hot and it would stay there. Okay, now water actually isn't a very good conductor of heat, so the water at the bottom would stay cold for quite a long time. Okay, so in a kettle it's designed so the heating element is at the bottom. Let's go up to the slide so to look at some other examples of convection. Okay, so we've got a mushroom cloud from an atomic bomb that's similar to the volcano there. So hot gases at the bottom expand, they rise, okay, and actually cold air takes its place. When there's been an atomic explosion, you sometimes get a firestorm. Cold air gets sucked in very fast, can generate winds of 200 or 300 miles per hour. Okay, we've got convection currents inside the Earth. Okay, so the centre of the Earth is very hot, the warm magma rises, cold magma falls, and of course it's this circulation that causes the slabs at the top of the Earth to move about. Okay, and that's why we have earthquake. Okay, here's similar to the kettle. This is a hot water system in a house. The heat is at the bottom, so the hot water rises, cold water takes its place, we get a convection current. Okay, in a house, certainly if you go to the UK, many houses have what we call radiators. Not really very well named actually, because they're very bad at radiating heat, which we're going to talk about next week. But they do heat the air next to them, the hot air rises, cold air falls, and so we get a convection current. All the air in the room gets warm. This is a lava lamp. In fact, it's wax and water. Okay, there's a hot lamp at the bottom. The wax expands, it gets less dense, it rises, cold wax falls. Lots of things in the kitchen rely on convection current. So again, similar to the kettle, you know, when we heat a liquid in a saucepan, the hot liquid rises, the cold liquid falls. If the liquid's too thick to move like that, so a very thick soup, that's why we have to stir it. And finally, this is an example of a sea breeze. Okay, so during the day the sun heats the land and the water up, but land heats up faster. We're going to talk about specific heat capacity soon. Oh, it goes faster, so the warm air rises from the land, cold air takes its place from the sea. And that's why when you look out to the ocean during the day, the breeze tends to be in your face. We call it the sea breeze. Okay, now the opposite does happen, of course. Hot air rises, that means cold air falls, which is why the coldest part in a refrigerator is actually at the bottom here, okay, where the cat is. Okay, I know sometimes it has a freezer bit at the top, but that's a separate part. Yeah, but generally the coldest part of the refrigerator is at the bottom because the cold air falls. Okay, so heat cannot travel in solids by convection. If you want to pause that and just think about why. Yeah, well, it's obviously because the particles can't move. Okay, so here are 8 sentences describing convection, but in the wrong order. So again, when this video is finished, if you want to go back to this, I'd like you to put these sentences in the correct order. Okay, so think about it first before you start writing. Okay. Okay, and finally, the piece of work to go with this is a what-if sheet. Now, I don't think we've done this before, so let me show you the worksheet. I want you to imagine what would happen if hot fluids no longer did rise, if there were no such things as convection currents. So here's today's newspaper. This is the Times of London, Monday the 30th of April. And scientists have discovered this morning that convection currents no longer occur. So less dense liquids and gases no longer rise. So I want you to think, so you're going to have to edit this is a Word document, about possible consequences. So you need to go back through those slides and think about how is life going to be different if hot liquids didn't rise. Okay, there's a special section here for the cooking correspondent. I've mentioned already there's lots of convection occurs in kitchens when you're cooking. And of course, looking long term, if this was true, would life be able to survive and why? So how would long-term life, so things will be a bit strange in the short term, but in the long term, could life survive on Earth? Okay, so what you need to do now is to go back on the video and copy those 2 slides of notes and then fill in this sheet, convection stops. What would happen if convection no longer happened? Okay? I'll try and stop it.